Hello, everyone. Back again for the third in our series of screencasts on section 5.3, hypothesis tests for a single population proportion. As promised, we are now going to review the hypothesis testing procedure one more time, dividing it into a series of organized steps as the textbook does. So I thought that for this example, we might use, instead of summarized data from some description of a situation, let's use some data from a data set provided by the TigerStats package. The data set is GSS 2012. So let's go ahead and head to RStudio and learn about it. So the way you learn about a data set from a package is that you ask to view it and you ask for help on it. So I'm going to run the command down here, view GSS 2012. And I'll also ask for help, parenthesis, GSS 2012. I'll get help over here. And let's first take a look at the help. So I'll get myself out of the way. And perhaps also make the screen a bit bigger. There we go. So the General Social Survey is run every 2 years out of an institute associated with the University of Chicago. And each year they interview thousands of people around the country and ask them very many questions. Not everybody is asked every question, but you tend to get a lot of responses on any single question. And these tend to be United States adults. And one of the questions that people were asked in 2012, it's a question they ask typically every time, is what's your opinion on capital punishment? And the responses are in this variable kapun. So if we were to look at the view and come on over, then we see kapun here. And I'm sorry, I actually accidentally sorted everything. But people could say they opposed, people could say they favored, and people could also not answer or not be asked the question at all, in which case they had an NA for their response. Let's go ahead and make this small again and head back to the slides. So if you're interested in how they responded to the question on capital punishment, then you could use the tally function, where the variable you're interested in is kapun, the data set it lives in is GSS 2012. You'd want to just kick out all of the NA responses so that you're only looking at the favors and the opposes. And we'll get the total number of people who answered the question as well. And so we see the results down here. Out of 1,824 people who answered the question, 1,183 of them favored the death penalty. So our question is, does that data constitute strong evidence that a majority of United States adults favored the death penalty in 2012? We have the sample, we're wondering what it's like out there in the population. So when you undertake a test of hypothesis, your first step should be to prepare for the test. And preparation involves several things. You first want to identify the population parameter that you're interested in knowing about. Then you want to write out the null and alternative hypotheses, those views about the value of the parameter. You want to make sure that you have a level of significance in mind. That's the cutoff value for when to reject the null hypothesis. And then you want to take a look at your data and identify the sample proportion and also the sample size n, as those will be useful in your calculations. So in our preparation step, we need to identify the parameter of interest. We want to give a nice complete sentence that defines the population parameter in words. Yeah. So here we go. Let P be the proportion of all United States adults who favored the death penalty in 2012. All United States adults, the entire population, as opposed to the sample. We know what happened at the sample. Make sure when you identify a population parameter that you make it clear what the population is from which you have sampled. Next, you want to write out the null and alternative hypotheses for your situation. Now, we were wondering whether the data provided strong evidence that a majority of the population favors the death penalty. So it makes sense to think about the boundary line between majority and minority, and that's 50%. So we'll have the null hypothesis say that P is 0.05. So that's equivalent to saying that neither a majority nor a minority of all US adults favor the death penalty. And the alternative hypothesis just disagrees with that. Remember, the null hypothesis is always going to be the one that claims that P is equal to a specific value. The alternative hypothesis in our course is always going to be two-sided. It will say that the parameter is not equal to that particular value. So, next bit is to identify our significance level alpha. This is a very easy step for us because we agreed earlier that we're going to stipulate that the level of significance is going to be 0.05 unless we say otherwise. So our plan is, if our p-value turns out less than that, we're going to reject the null hypothesis. If our p-value turns out bigger than that, we're going to fail to reject the null. Okay, well, let's now identify our data, or identify the summary statistics from our data. What's the sample proportion? What was the sample size? Well, looking back at the tally that was provided, we can get the sample proportion. P hat is the 1,183 people who said, yes, I favor capital punishment. 1824 is our sample size, and so we record that sample proportion in a variable in R. How about P hat? And let's also go ahead and record what the sample size is. N is 1824. Now we're on to the step 2 in our overall process of hypothesis testing. This is the check step. This is the step where you check to see if the hypothesis testing method that you plan to use really does fit your data situation. We need to verify the conditions to ensure that the distribution of the sample proportion is approximately normal. Our p-value computations relied on the probability distribution being normal. We were using p-norm GC, remember. So we need to check and see if in this situation, p hat's going to really have a normal distribution. So for this, we can use the success failure condition, and we check it out, and we see the number of successes is 1,183. That's definitely at least 10. The number of failures is 641. That's at least 10. So we should feel fine about using the normal approximation to get the p-value. Just want to make a quick note here. The textbook says that you ought to base your check of the success failure condition using the null value p naught. And so if you did do it that way, the expected number of successes would be the n times 0.5, which is, of course, bigger than 10. The expected number of failures would be the sample size times 1 minus the p naught. Again, that is bigger than 10. There's good arguments to be made for both approaches, working with the null value versus working with the observed successes and failures. We're just going to stick with the success failure condition as we learned it earlier. I'm not going to require you to switch over to this method just because we're dealing with a hypothesis test now. Step 3 in the process of a test of hypothesis is to calculate, find the value of your test statistic, and then find the p-value from that. So in order to get the test statistic for our situation, you remember that it has the standard error for p naught in its denominator. So we're going to, the standard error for p hat in its denominator. We're going to have to get that value initially. Then we can get the z statistic. Then we can go on to get the p-value. So let's get that standard error. Well, the null thinks that p is 0.5, so the standard error for p hat, under this temporary assumption that the null is right, is given by the math formula you see here. So in R, we just do the square root of p naught times 1 minus p naught divided by the n that we set up, the 1824, and it's about 1.1%. So we can get the z-score. That's our test statistic. The p hat minus the null's belief of 0.5 divided by that standard error turns out to be 12.6. My goodness. So the sample proportion that we got in this data is more than 12 standard errors above what a believer in the null hypothesis would expect. That seems really unlikely. A really unlikely thing to happen if the null is right. But let's find how unlikely by computing the p-value. That's the next part of this compute step. Because we've checked that the sample proportion has about a normal distribution, we get to compute the p-value using p-norm GC. Now, we had set up a little variable z to contain the test statistic, so let's just use that z as our boundary, ask for region outside, and don't forget it's the standard normal curve that we're using here as the distribution for the test statistic. So set your mean to 0 and your standard deviation to 1. Ask for a graph if you like, and you get this result here. So you get that standard normal curve, and then poor old R, it's having to draw a minus 12.6 up to a 12.6. So that's way, way, way far out in the tails of this standard normal curve. The total area under the standard normal curve outside of those two values, minus 12.6 and 12.6, is so tiny that you just can't even see it as a shaded area. And it's approximated as a 0 up here in the title for the graph. But in your console, you're going to see a more exact statement of what they think the p-value is. 6.6 times 10 to the minus 37 power. Now remember, that's R's way of talking scientific notation. So let's review that just for a moment. So, when you see stuff like this coming out from R, remember that it's scientific notation. The E basically stands for 10 to a power. And so that number really is 6.5 times 10 to the negative 37 power. That's 6.5 divided by 10 to the 37 power. That's 6.5 divided by a 1 followed by 37 zeros, an enormous number. So 6.5 divided by this enormous number is a really, really small number, very, very close to zero. And so when you see this sort of number where there's like a high negative after the E, you know that that's a number that is positive, but really, really close to zero. And so the p-value is really close to zero. The big deal is to interpret the p-value in the context of the problem. And that's done by writing out a complete sentence, where the basic template is, if the null is right, then there is about a, whatever the p-value is, chance of getting results as at least as extreme as the ones we got in our study. So one way you might write it out here is, if neither a majority nor a minority of the population favors the death penalty, that's the statement that the null is right, then there is about a really small p-value chance, 0% chance of getting a test statistic at least as big as the one that we actually got. And now we can think ahead to what this leads us to. We actually got this z is 12.69. So, gee, this looks really bad for the null hypothesis. That takes us to step 4 in the standard process for a test of hypothesis. Step 4 is the conclude step. All you have to do here is compare your p-value to the level of significance, alpha, that you had set up, and then reject or fail to reject based on that comparison. Remember, reject if your p-value is less than alpha. Fail to reject if it's bigger than alpha. And then you'll want to write down a simple conclusion, stated in the context of the problem, saying how much evidence the data provide against the null hypothesis. So for us, the p-value was about 0, and that's less than 0.00, that's less than 0.05 for sure. So our decision is going to be to reject the null hypothesis. We're going to rule out as unreasonable anybody who thinks that 50% of the US population favors the death penalty. Our little one-sentence simple conclusion is that the data provided extremely strong evidence. I said extremely strong because the p-value was so small. Extremely strong evidence that a majority of US adults in 2012 favored the death penalty. And that's because in the data, I saw a majority favoring the death penalty. The 1,100 who favored the death penalty was more than half of the 1,800 who were asked the question. The p-hat was bigger than 0.5. So you'll often do that in your conclusion. You'll talk about which direction of the alternative hypothesis the data is leading you to. Now, I'll just point out that you could get the same conclusion off of a 95% confidence interval for P. That's because of that relationship between confidence intervals and tests of hypothesis that we looked at in the last screencast. So if you were to just write in the R code to make a confidence interval, then your formula for the standard error needs to change a little bit, because when you're making a confidence interval, you're not working with a null value. You're just going to estimate the standard error with the sample proportion. So we do square root of p hat times 1 minus p hat over our sample size. And then The margin of error for a 95% confidence interval is 1.96 times the standard error, so we subtract that off of our sample proportion, and we're down to 62%. If we add it on to our sample proportion, we're at 67%. 62% to 67%. The null value is that p is 0.50. 0.50 is way underneath all of the numbers in that interval from 0.62 to 0.67. So the null value is not a plausible value for p based on the data. And we could say that we've got a lot of evidence that p is bigger than 0.5. So you can get the same result off of a confidence interval. This sets the template for a lot of our future work. We're going to be thinking about other parameters for populations and other types of data analysis situations. And we'll be learning about other hypothesis tests for those situations. And the formulas and the computations that you're going to do are going to be different. And good news coming up, the computer is really going to do most of those computations for you. You're not going to have so many computations they have to write in by hand using R like a calculator. That was just kind of an introductory thing for this chapter. But the basic procedure is going to be the same. You're going to have a prepare step where you define a parameter of interest, state your hypotheses, and set up whatever summary data is going to be needed for the test. You're going to need to check some conditions for the test to be reliable for most of the tests that we do. You're going to have to look at what R gives you for the test statistic and the p-value. And you're going to have to use that to draw your own conclusion as to whether you're going to reject or fail to reject the null. And you're going to need to write that simple conclusion about how much evidence the data provided this time against the null hypothesis. That's it for the screencast of section 5.3. So we will see you later.